Until recently, all eyes were locked on one anomaly, 3I-ATLAS, the third officially confirmed interstellar object to enter our solar system. Its peculiar structure, excessive carbon dioxide signature, and unexplained symmetry have drawn headlines since early October. But on the morning of November 28th, something else appeared in the data stream. A second object, less discussed but equally confounding, began exhibiting behaviours impossible to ignore. The SWAN object, initially flagged by the Solar Wind Anisotropies SWAN instrument aboard the SOHO satellite, was first assumed to be a harmless solar wind artefact. But as data continued accumulating, one fact became clear. This was not just noise. It was a body, moving fast, accelerating slightly, and now entering a resonant orbital band similar to that of 3I-ATLAS. What makes this discovery extraordinary is not just its timing or its proximity, it's the profile. SWAN's thermal emissions, detected independently by ground-based observatories in Chile and infrared monitors on the ISS platform, show something rare. A low-albedo object emitting consistent but cold infrared radiation with symmetrical plasma halos. It has no distinct tail, unusual for any cometary body, and most importantly, its light curve oscillations match a profile we've only seen once before, in the early tracking phases of 3I-ATLAS. That's not supposed to happen. Two interstellar bodies, both exhibiting non-standard acceleration and unique energy distribution, converging near Earth's orbital zone within the same month, is statistically improbable. The designation SWAN is still temporary. It's not yet been fully classified by the Minor Planet Center, largely because its origin vector is still uncertain. The anomaly emerged in a lower observation corridor just past Earth's magnetic bow shock, where data tends to get lost in solar noise. It was only after recalibrations from ESA's solar physicists that the object's motion became distinguishable from background solar wind turbulence. What they found startled the room. A stable trajectory with slight perturbations, enough to suggest minor internal propulsion or volatile-driven acceleration. The shape of the energy signature surrounding SWAN was spherical. Not cometary, not a flare, a thermal sphere, expanding evenly. That type of uniformity requires explanation. What we do know is this. Its estimated velocity is slightly slower than 3I-ATLAS, but follows a similar inbound arc. The expected perihelion is not yet known, but its current path suggests a non-elliptical hyperbolic vector, just like 3I-ATLAS. In other words, this isn't from our solar system, and it's not staying. That's what makes this moment urgent. Interstellar objects do not behave like solar system comets. They don't circle back, they enter once, and then they leave, unless they fragment, collide, or alter course. Several researchers, including those at the University of Arizona and an independent analysis team in Singapore, have pointed out a concerning detail. The plasma harmonics surrounding SWAN appear to be mirroring a rhythm observed near the heliospheric current sheet, a rippling magnetic boundary where solar polarity flips. In short, SWAN is reacting to local forces in ways that imply sensitivity, not passivity. This is not behaviour we associate with inert objects from deep space, especially not at this scale. And here's the core problem. 3I-ATLAS was already rewriting the rulebook. But now, with SWAN entering the scene and beginning to mirror the same anomalies, we are no longer looking at an isolated event. We are looking at a convergence, two unknowns in tandem inside our system, drawing closer to Earth's orbital path. They may not be on a collision course with our planet, but they are colliding with our assumptions. And on the morning of November 28th, the first composite models of the SWAN-ATLAS alignment became available. What they showed was subtle, but unmistakable, a pattern, a resonance, and perhaps coordination. Silence in astronomy is rarely just silence. More often, it's a signal in disguise. And when it comes to the object now unofficially labelled as SWAN, its silence is what has triggered some of the most urgent late-night calls between observatories across 3 continents. Unlike 3I-ATLAS, which has provided a visual trail of escalating anomalies, tails, jets, asymmetric glows, and radiative flares, SWAN has remained, in a word, mute. No optical tail, no visible outgassing, no dramatic spikes in brightness. In short, nothing to confirm that what we're observing is a comet in the traditional sense. But therein lies the problem, because the instruments say otherwise. The mass is real, the trajectory is measurable, the infrared signature is constant, and yet to visible light telescopes, even those with high angular resolution, SWAN appears ghost-like, borderline invisible. This optical void is deeply unsettling to mission analysts. Normally, when an object enters the inner solar system, solar radiation triggers volatile materials on its surface to sublimate. This process produces visible jets of gas and dust, forming the familiar tail that marks an active comet. But SWAN is doing none of this. In wavelengths our eyes depend on, it has failed to emit anything that would visually identify it as a cometary body. It remains an empty centre surrounded by soft electromagnetic disturbance. This leads to two options, both concerning. The first is that SWAN is heavily cloaked in non-reflective material, possibly carbon-rich, forming a shell so dark it deflects nearly all visible light. Some solar system bodies, like Comet 67P, have exhibited low albedo, but never to this extent. SWAN's current albedo readings are below 0.01, darker than coal. That would mean it is either coated in a fine layer of dust compacted over millennia, or its outer shell is composed of material designed to avoid detection. And this is not speculation. It's modelled from thermal infrared data that clearly shows heat, but no light. The second possibility is more disturbing. That SWAN is not emitting light because it's not interacting with solar radiation the way normal comets do. There are no signs of sublimation, no dust trails, no jets. In fact, it's entirely possible the surface isn't sublimating at all, because there may not be ice to sublimate. The implications of this would upend the classification entirely. If SWAN is inert, then it should be gravitationally static, but it's not. Minor accelerations traced over 10 days of infrared positioning suggest that something is subtly altering its motion, something internal, or something controlled. What makes the silence even more chilling is that it contrasts sharply with the rest of the electromagnetic profile. The SWAN object has a consistent low-frequency hum detectable by radio telescopes monitoring long wavelength emissions near the solar equator. While not a signal in the communicative sense, this pattern is rhythmic and recurring. Yet none of this shows up optically. The result is a mismatch, a deeply precise anomaly with mass and motion, but no image. Professional observatories like Mauna Kea, Cerro Paranal, and the Indian Astronomical Observatory have confirmed that even under optimal viewing conditions, the object remains visually silent. Only instruments tuned to the microwave and thermal spectrum see the outline. It's like watching a car race through fog, only visible through the heat it throws off, never through its actual headlights. And here's what keeps being whispered behind closed doors. When something large, fast and cold chooses silence in the part of the spectrum we've relied on for a century, it's either new physics or it's hiding. The lack of optical activity may not be an accident. It may be part of the object's physical makeup or intentional design. Because nature tends to be loud when it melts, breaks, spins or reacts. Silence, in contrast, requires control. And that's why observatories aren't just confused, they're afraid. Most interstellar objects that pass through our solar system do so at odd, tilted angles. Their paths cut through the planetary plane like skewed arrows, entering and exiting before we can even observe their full rotation. But something different is happening with 3I-ATLAS and the newly tracked SWAN object. Their trajectories are converging, not just in physical proximity, but inside a very specific spatial layer, the Earth's orbital plane. This orbital zone, often referred to as the ecliptic, is a flattened disk where nearly all planetary motion occurs. It's where the Earth, Mars, Venus, and all other inner planets revolve around the Sun in neat, predictable ellipses. Comets and asteroids that originate from our solar system tend to follow this plane loosely. Interstellar objects almost never do. That's what makes this moment historic. Two hyperbolic objects, both confirmed to have non-solar origins, are now intersecting this corridor at near-synchronous timing. This shared entrance into the ecliptic is not just a geometric coincidence, it carries consequences. From a dynamic systems perspective, the ecliptic is not a passive space. It is threaded with electromagnetic filaments, solar wind compression zones, and the influence of planetary gravity wells. Objects moving through it experience interactions that do not occur at higher orbital inclinations. The ecliptic is where forces compound. Radiation pressure, gravitational focusing, plasma density. everything intensifies in this layer. So what happens when two high-velocity interstellar-class bodies begin operating within that same corridor? The first consequence is mutual resonance. While the two objects are not gravitationally bound and will not physically collide, their proximity within a shared corridor creates the possibility for resonant wave interference. This has already been seen in preliminary magnetospheric readings. Microfluctuations in the solar wind measured near Earth's bow shock show a strange double frequency pattern. Some speculate this may be interference between SWAN's thermal envelope and ATLAS's trailing plasma tail. The second consequence is observational. Objects in the ecliptic are far easier to observe from Earth-based facilities. That means more frequent measurements, higher resolution data, and faster detection of changes. But it also means any energetic interactions, outbursts, fragmentation events, or accelerative shifts are more likely to have an impact on near-Earth space weather. Then there's the geopolitical consequence. Multiple agencies, including NASA, ESA, JAXA, and the Chinese National Space Administration, have scheduled overlapping observation windows for both SWAN and ATLAS. The level of international coordination is unprecedented for two objects that are not classified as threats. That suggests something unspoken. Agencies may not fully understand the potential outcomes of two interstellar visitors coexisting in a shared energy corridor. And perhaps most interesting of all is the emerging theory that this convergence was not random. Some physicists have begun modelling the trajectory of both objects backward in time, and a pattern has emerged. If one projects both ATLAS and SWAN to their origin vectors, millions of years in the past, they appear to emerge from roughly the same angular quadrant of local interstellar space. The trajectories are not parallel, but they converge near a point of origin somewhere within the Scutum Centaurus arm. This has led to a growing hypothesis that ATLAS and SWAN may be fragments of a larger system, or worse, cooperative bodies from the same ejection event, launched or expelled together, only now beginning to operate in parallel under the gravitational structure of our Sun. Whatever the case, their presence in the ecliptic cannot be ignored, because this is not just a passing intersection of paths, it's an activation zone, a region where interstellar variables meet solar system laws and neither behaves the way it's supposed to. The last time one object entered this corridor, Oumuamua, it left without answers. This time there are two, and they're not just passing through. In space, heat is never just heat. It's a signature, a code written in infrared. And when it comes to interstellar objects like 3I-ATLAS and SWAN, that code is what scientists rely on when everything else is either invisible or unresponsive. But over the past 3 days, instruments across multiple observatories began reporting something that should be impossible: thermal correlations between two separate objects with no known connection, separated by millions of kilometers. The early warning came from the Very Large Telescope, VLT, in Chile. Using its upgraded thermal imaging spectrometer, it captured narrowband heat emissions from 3I-ATLAS that oscillated in short, repeating pulses. Nothing unusual at first, but the exact same frequency pattern was then detected coming from SWAN, roughly 10 hours later by the Subaru telescope in Hawaii. Identical thermal pulses, staggered in time but mathematically consistent. These two objects should not be communicating. They should not be interacting. And yet, their heat maps are suggesting otherwise. So what exactly is being detected? Let's step back. Both 3I-ATLAS and SWAN are surrounded by tenuous atmospheres, comas composed of gas and dust, some naturally formed through sublimation, and others through unexplained mechanisms. These comas emit in infrared due to the energy absorbed from the sun. Normally, you would expect the intensity and structure of those emissions to be determined by distance, composition, and rotational dynamics. But in this case, something more complex is emerging: pattern matching. High-resolution thermal data shows that both bodies are exhibiting fluctuating hotspots on their surfaces. These hotspots are not static. They shift in a wave-like rhythm. On 3I-ATLAS, the pulses seem to move along its equator. On SWAN, the pattern rotates more slowly, but in sync with the same waveform envelope. That's a statistical anomaly with less than a 0.1% chance of being random. And the pattern is not smooth. It repeats in segments: 3 short pulses, a longer delay, then a broader flare. This sequence has now been captured by infrared observatories in 4 independent locations. If this were thermal noise or internal dynamics, the patterns would be unique to each object. but the matching profiles imply either simultaneous internal mechanics or some form of external synchronization. The first theory posited by the European Space Agency's infrared modelling group is what they call a solar harmonics cascade. In this scenario, both objects are responding to the same upstream solar trigger, perhaps a wavefront, in solar radiation or a localized shift in the heliospheric current sheet. That could explain similar thermal behaviors even if the objects are not physically interacting. But that theory runs into a problem: distance and delay. SWAN's pulses are arriving too late to be reacting to the same solar event that triggered Atlas's emission, and yet the patterns match not just in sequence, but in amplitude decay. That suggests that either SWAN is echoing Atlas, or both are responding to something non-local, something systemic that propagates across space faster than thermal energy alone. This has led some to a more controversial idea, that the heat patterns are a form of energetic resonance, not a signal in the communicative sense, but a passive synchronization, like two pendulums swinging in rhythm after being suspended from the same beam. Could 3I-ATLAS and SWAN be operating under similar internal processes? Processes that, when introduced into the same solar environment, begin to resonate? Or, and this is the hypothesis no one wants to say out loud, could one be reacting to the other? Because if SWAN is mimicking 3I-ATLAS's heat pattern with time delay, that implies reception. That implies awareness, thermal, magnetic, or otherwise. And here's where the discomfort sets in. These are not fragments from the same comet. They're not captured asteroids. They're two hyperbolic interstellar bodies, both behaving in ways that break thermal models and now mirroring each other in the invisible spectrum. We often say space is cold, but the silence isn't what matters here. It's the warmth and the pattern inside it. In astrophysics, 6 seconds is usually nothing. A rounding error, a data hiccup, a minor calibration drift you dismiss unless it happens again. But on November 24th at 02:13 UTC, 6 seconds became the centre of a cascading concern within the European Space Agency's Solar System Dynamics Division. The initial problem began with something routine, triangulating the updated position of the SWAN object. SWAN had just crossed into a higher resolution tracking corridor, allowing ESA's Near-Earth Object Coordination Center, NEOCC, to attempt a more precise orbital refinement. The process was simple. Combine 3 independent observations, one from ESA's Deep Sky Monitoring Station in Tenerife, one from the solar-aligned Lagrange 1-point via SOHO's SWAN camera, and a third from the optical guidance array on board the Bepi-Colombo spacecraft. Each of these observatories recorded SWAN's position within milliseconds of one another. But when engineers ran the standard light time correction and plotted the vectors, something didn't fit. The predicted alignment of the object was off, not spatially but temporally, by 6 full seconds. That is, SWAN's apparent position only made sense if it had been slightly further along its trajectory than expected. Not only did this indicate movement that contradicted gravitational models, but it did so in a way that none of the instruments had flagged as anomalous. Here's what that means in real terms. SWAN moved further in those 6 seconds than it should have, assuming purely passive motion through the solar system. No gravitational assist, no outgassing event. No nearby body to influence its course. Just a drift, subtle, silent, and until now, unnoticed. At first, ESE's internal review assumed a clock desynchronization issue. Perhaps the onboard timing of Bepi-Colombo or the Earth-based observatories was misaligned. But when timestamps were cross-verified with ground station logs and satellite telemetry, everything checked out. The clocks were accurate. The error wasn't in timekeeping. It was in the position of the object. That's when the alarm bell started ringing. This 6-second drift indicated a very small but highly precise non-gravitational acceleration. In fact, the velocity offset required to explain it was roughly 0.028 meters per second squared, a value far too small to be caused by any known reaction forces, and yet far too large to be ignored in orbital calculations. The implications are twofold. First, it suggests SWAN is not passively coasting. It is experiencing or generating a consistent low-level force, the kind of sustained acceleration that, if extrapolated, could shift its trajectory by tens of thousands of kilometers over the next month. That's enough to completely invalidate any predictive model for its perihelion or Earth relative distance. Second, and more disturbingly, the force is unidirectional. The object isn't tumbling, spinning randomly, or releasing jets that produce stochastic motion. It's drifting forward on a clean vector, with none of the visual cues, outbursts, tail wobble, or coma dissymmetry that usually accompany motion driven by sublimation or venting. This event mirrors an earlier incident involving 3I-ATLAS, where NASA's deep space navigational models had to be adjusted after a persistent transverse acceleration was detected. But that case at least had partial visual correlates, jets, fluctuations in coma brightness, and heat asymmetry. SWAN has none of that. Its drift is occurring without observable propulsion. Some have quietly compared this to the infamous Pioneer anomaly, a small unexplained acceleration detected in early NASA deep space probes, later attributed to thermal recoil force. But SWAN isn't a spacecraft. At least it isn't supposed to be, and yet it behaves like one, with no obvious thrusters, no rotation, and now a drift that violates the gravitational map we've built the entire solar system around. It's too early to call it a propulsion signature, but it's not too early to say this. ESA's triangulation error wasn't a mistake. It was a discovery of something moving with its own rhythm, not faster, not louder, just slightly ahead of schedule, 6 seconds ahead. There's a quiet but growing theory that's beginning to circulate behind the scenes, one that challenges not just what 3I-ATLAS is, but how we define the structure of interstellar objects entirely. It's called the hollow core hypothesis, and as of November 28th, it's no longer being whispered only in theoretical papers. It's now being applied to SWAN. The hypothesis began with 3I-ATLAS. Early infrared absorption data from the James Webb Space Telescope showed peculiar layering in the thermal profile. Thin radiative zones followed by rapid drop-offs, then secondary echo zones deeper inside. At first, this was attributed to compositional stratification, surface ice, dust mantle, then perhaps a denser rocky core. But that didn't align with its behaviour. The object was too light for its projected volume, too reactive to shallow sunlight, and, most curiously, too structurally stable during its pass through the inner heliosphere. All of this led to a new proposal, that Atlas's centre wasn't dense, it was empty, or at least less than solid. In simpler terms, a shell, not a ball. Hollow cores are extremely rare in natural solar system bodies. Gravity tends to collapse internal voids in anything larger than a few kilometres, but Atlas appears to be resisting that trend. If it truly is interstellar, then it could have formed in a completely different gravitational thermal environment, one where pressures, materials and energy budgets allowed for a completely different structural outcome. Now here's where things become more complicated and more fascinating. Over the last 72 hours, preliminary heat absorption data from SWAN, captured by the Stratospheric Infrared Observatory Network, SION, using mid-range spectrometry, show the same hollow signature: low external absorption, thin thermal delay, then a second, fainter thermal ring approximately 1.8 kilometers beneath the surface. That's not what you see in solid cometary nuclei. It's what you'd expect in a layered shell: dense outer material, air gap or vacuum, then a deeper, possibly active surface. To explain that, researchers began running density simulations based on the object's infrared mass signature. The models showed something eerie. If you remove the assumed core from SWAN and calculate the mass from just the shell, the observed acceleration and drift begin to make more sense. In other words, SWAN's slight forward push, like that unexplained 6-second lead, is consistent with a low-mass object being moved by a very small internal force, perhaps pressure equalization inside a chambered body. One working theory is that the interior of both 3I-ATLAS and SWAN may contain trapped volatiles, not in random pockets like typical comets, but in geometric distribution across an inner wall. In the case of Atlas, sudden pressure equalization during perihelion could have activated jets all across the interior edge. In SWAN's case, the pressure gradient may be subtler, producing drift without explosive, outgassing. Now comes the philosophical question. What would naturally form a hollow object this large, and why? Some astrophysicists suggest it may be a byproduct of interstellar grain agglomeration. If dust and gas accumulated around an early solid core, and that core sublimated or vaporized over time, perhaps by cosmic ray exposure or micrometeorite erosion, It could leave behind a hollow shell. Another more radical possibility is artificiality, that these objects, or at least their structural features, were engineered. It's not necessary to jump to that conclusion, but it is necessary to note that hollow structures offer certain efficiencies: mass reduction, structural symmetry, and low gravity maneuverability. In spacecraft design, those are all advantages. Still, we must stay grounded. There is no direct evidence of construction, no signals, no manufactured surface patterns, only behaviour and structure that seem inconsistent with solid body physics. But when two unrelated interstellar objects, arriving within the same quarter, on similar vectors, both show signs of internal voids, you can no longer treat that as coincidence. The hollow core hypothesis is no longer just a fringe model for 3I-ATLAS, it now applies to SWAN, and if two hollow bodies are entering the ecliptic corridor together, one question becomes more urgent than ever. What exactly is inside? Plasma is often described as the fourth state of matter, an electrified fog of stripped ions and electrons that behaves as much like a field as it does like a fluid. But when you compare the plasma environments of two different interstellar objects entering the same solar corridor, you expect variation. You expect noise. What you don't expect is symmetry. That's exactly what's happening with 3I-ATLAS and SWAN. According to the latest high-resolution spectrographic data from NASA's Magnetospheric Multiscale Mission, MMS, the plasma envelopes surrounding both bodies are not only similar, they're behaving like matched signatures. Each field exhibits a layered sheath of low-density ionized particles, a thin boundary zone of magnetic deflection, and then a deeper, denser core with rotational charge drift. This shouldn't be happening. Let's start with the basics. A normal comet produces a plasma tail as it approaches the Sun. Solar ultraviolet radiation ionizes the gases in the coma, separating electrons from their parent molecules. These ions then get swept away by the solar wind, forming a plasma tail that points directly away from the Sun. But both ATLAS and SWAN have refused to play by those rules. ATLAS's plasma tail doesn't point directly away from the Sun, it spirals. Spectropolarimetric analysis shows a subtle rotation pattern in the charged particles, as if the tail isn't just being pushed, it's being guided. Worse, its polarity flips erratically, producing what the ESA plasma division has called phase reversal drift. That term has no precedent in cometary physics, it was coined specifically for this case. Now fast forward to SWAN. Despite having no visible tail, SWAN is surrounded by a faint but measurable plasma sheath. It's been observed in both the extreme ultraviolet and low-frequency radio domains. What's unusual is that SWAN's sheath mirrors the same field layering as ATLAS, down to the electron density taper and frequency of magnetic fluctuations. The frequencies match within 3.7%. For two unrelated bodies, that's not just a match, it's a pattern. And here's where it gets stranger. When the Parker Solar Probe flew within triangulation range of both objects' outer plasma fields, it detected what researchers called correlated induction echoes. In plain terms, small magnetic surges in SWAN's sheath were mirrored seconds later in ATLAS's field. Then the reverse happened. Not exact duplications, but delayed responses, interactions like soft pings across space. What could cause this? One suggestion is environmental coincidence. Perhaps both objects are travelling through a shared band of turbulent solar wind or embedded heliospheric current sheets, and that shared medium is responsible for harmonising their field behaviour. It's a conservative hypothesis, and also incomplete, because models that simulate solar wind variability at the current object distances fail to recreate the precision of the mirrored oscillations. Another theory is rotational electromagnetic resonance. If both SWAN and ATLAS have internal magnetic cores, or hollow chambers charged with ionized gas, they might function like low-frequency LC circuits, emitting weak radio pulses as they rotate. Those pulses, if close in frequency, could align into constructive interference that could in turn produce the observed plasma field echoes. But that raises its own questions. Why would two objects, originating from different parts of interstellar space, have matching electromagnetic oscillation frequencies? Nature is rarely that symmetrical, and plasma is rarely that consistent. Which leads to the final and most controversial theory: controlled plasma shaping. In artificial spacecraft, plasma fields can be shaped by embedded coils or surface charge differentials, essentially magnetic sails. If either object possesses such features, even incidentally, it might allow for minor adjustments to its plasma tail orientation, or even thrust vectors. We're not claiming propulsion. But we are seeing behaviour that mimics it. Steering, not trailing. Shaping, not shedding. To be clear, no direct signs of technology have been detected. No straight edges, no manufactured materials, no clear emissions beyond what's been described. But what's undeniable is this. Two different objects should not have matching plasma fields. Their dust content, trajectories, and thermal histories are too distinct. Yet here they are, layered, harmonised, reactive. And if their fields are interacting even weakly, then these objects are not travelling alone. They are, somehow, travelling together. A comet without a tail is like thunder without lightning, visibly incomplete and physically unsettling. Since the earliest days of astronomy, comets have been recognised by their brilliant tails, luminous streams of dust and ionised gas stretching millions of kilometres behind them as they arc toward the sun. These tails are not optional, they're fundamental to what defines a comet. So when SWAN, an interstellar object accelerating into the inner solar system, fails to exhibit even the faintest sign of a tail, the question is no longer observational, it's existential. What does it mean for a supposed comet to show no tail at all? The first explanations were technical. Some astronomers suggested it was a matter of angle, that perhaps SWAN's tail was pointing directly away from Earth and simply hidden in its own bright coma. But spectral analysis ruled that out. The coma wasn't bright enough, and more importantly, there was no directional bias in the electromagnetic scattering. No tail-shaped density fall-off, no asymmetry. Just a soft, uniform glow in infrared and near-ultraviolet, almost spherical, with no trailing debris. Others pointed to material composition. Comets in our solar system typically erupt with water vapour and dust. But SWAN, like 3I-ATLAS before it, shows an unusual dominance of carbon dioxide and carbon monoxide. These gases sublimate at lower temperatures and produce less dust when heated. In theory, a comet composed almost entirely of volatiles could shed gas without generating a visible tail, especially if dust grains are trapped or never ejected. But here's the contradiction. Spectrometers still show thermal activity. CO2 emissions are real. There is outgassing. So where's the trail? Infrared data from the Subaru telescope and the Infrared Survey Facility, IRSF, in South Africa reveal that gas is escaping, but not in any direction we'd expect. The emissions form a symmetrical halo, expanding evenly in all directions. It's not being shaped by solar wind, it's resisting it. This has led researchers to explore a possibility that goes beyond chemistry, active containment or cancellation. Plasma physicists reviewing the emissions noticed something curious. The outgassed particles are not drifting away freely. They remain close to the object, confined within a faint magnetic envelope. That behaviour mimics an induced magnetic field, the kind you'd expect from an object with internal electrical activity or highly conductive surface layers. If that's true, then SWAN isn't just lacking a tail, it's suppressing one. One working hypothesis is that the object possesses an electrically active crust or subsurface layer that creates weak localized magnetic fields. These fields could trap ionized gas in a shell-like configuration, preventing the solar wind from pushing it into a classic tail. Alternatively, if the outgassing is evenly distributed, perfectly symmetrical, it would create equal pressure in all directions, eliminating the differential needed to form a tail at all. Such symmetry is rare in natural objects, and here's the twist. 3I-ATLAS exhibited the same anomaly. During its closest solar approach, when it should have produced an enormous tail, it briefly reconfigured into a sphere of light, tailless, glowing evenly. That moment was dismissed by many as a transient flare, or even an imaging artifact. But now SWAN is doing the same thing, and doing it earlier, colder, quieter. So we must consider the broader implication. Are we witnessing a new class of interstellar object? A type of comet whose volatile behaviour is governed less by solar heating and more by internal structure? Or are we witnessing field manipulation, an intentional or evolved suppression of directional energy loss? Because in physics, energy never just disappears, it transforms. If these objects are not radiating motion in the form of tails, then that energy is going somewhere. possibly into containment, possibly into directionality, or possibly into a system we haven't yet identified. In the past, comets were omens, their long bright tails slashing across the sky as warnings. But now we see the opposite. Dark objects, silent, tailless, emitting nothing visible, yet still accelerating. Maybe this is the new normal. Or maybe this is what controlled energy looks like in deep space. Polarization is one of astronomy's most overlooked diagnostic tools. It tells us how light waves are oriented after scattering off a surface or passing through a medium. When light bounces off dust, gas, or ice, its electric field aligns in specific directions depending on the material's shape, texture, and composition. Every comet, asteroid, or planetary surface has a unique polarization signature, a kind of electromagnetic fingerprint. But SWAN's fingerprint doesn't match anything we've seen before. In fact, it's conflicting with the very physics we use to define natural light scattering. On November 25th, a team at the Roque de los Muchachos Observatory in La Palma, using a wide-angle polarimetric camera, collected high-sensitivity data on the SWAN object during its early morning transit. What they expected was a negative polarization branch, a familiar dip in polarization at small phase angles, when the object is nearly aligned with the Sun and Earth. That's standard for comets, as the light scattering off their dusty comas tends to polarize in predictable, well-documented ways. But SWAN didn't follow that script. Instead of the expected shallow dip, SWAN's polarization reached an unprecedented 2.9% at just 16.7 degrees, a value deeper than almost any comet or asteroid ever recorded. For comparison, most solar system comets hover around 1% to 1.5% in this range. Not only was SWAN's reading significantly deeper, but it also inverted sooner than expected, crossing the zero polarization threshold before 17 degrees. That's a full 5 degrees earlier than standard models predict. This anomaly, now referred to in internal reports as the SWAN polarization conflict, has raised red flags across the astrophysical community. The first interpretation was technical error. Could there have been a calibration fault in the polarimeter? Could the telescope's mirror alignment have introduced false polarization? But follow-up measurements from 3 other instruments, including the Pollux ultraviolet polarimeter aboard the Hubble Space Telescope, confirmed the reading independently. Different instruments, different wavelengths, same contradiction. So what does it mean? To answer that, we need to consider what causes polarization in the first place. When sunlight hits cometary dust, the particles act like tiny lenses or reflectors, aligning the light's electric field in preferred orientations. The resulting polarization tells us about the dust's size, texture, composition, and even whether the surface is fluffy or compact. SWAN's extreme polarization suggests that its dust, or whatever material surrounds it, is doing something drastically different. The particles may be much smaller than average, or more uniform in shape, or they may not be particles at all. One speculative theory suggests SWAN is emitting sheets or films of structured material, ultra-thin layers behaving more like diffraction gratings than dust grains. Another possibility is surface smoothing. If SWAN's outer shell is unusually smooth at the microscopic level, it could reflect light in a highly coherent fashion, amplifying the polarization signature. That kind of surface would imply thermal processing, maybe even melting and resolidification, something not usually associated with distant interstellar objects. Unless, of course, the object is internally active. But the most unnerving idea comes from a handful of plasma physicists. What if the polarization isn't a product of dust at all, but of electromagnetic influence? If SWAN is surrounded by a low-energy magnetic field, as Chapter 7 already suggested, then light travelling through that field could become polarized through an entirely different mechanism, magneto-optic rotation. In this scenario, the electromagnetic field itself bends the orientation of light passing through it, altering its polarization without needing dust at all. This has never been observed in a comet. It has, however, been observed in engineered plasmas, specifically ion traps and fusion containment fields. No one is saying SWAN is artificial. But many are now saying something else, that its wake, this invisible, unseen trail it leaves as it travels, carries with it a polarization pattern too coherent, too deep, and too early to be explained by dust alone. And in science, when you remove the known, what remains, however unlikely, demands attention. The light behind SWAN isn't just dim, it's aligned. By November 28th, most major observatories had placed SWAN firmly on their observation calendars. Its growing list of anomalies, silent plasma, hollow core signatures, polarization conflict, should have elevated it to priority status across all instruments capable of deep sky detection. But one telescope didn't issue any alerts. It didn't elevate SWAN to emergency tracking. It didn't trigger the usual data sharing protocols. That telescope was the James Webb Space Telescope. Why? James Webb is arguably the most powerful astronomical instrument ever deployed. Its near-infrared spectrograph, NIRSpec, and mid-infrared instrument, MIRI, are capable of detecting faint thermal emissions, compositional spectra, and structural irregularities with unprecedented precision. It has already captured surface temperatures on exoplanets, resolved dusty circumstellar disks, and spotted minor compositional changes in deep sky comets. So why didn't it see SWAN? The short answer is, it did. The longer answer is more complicated and more troubling. Internal telemetry logs from Webb's Cycle 3 targeting queue, leaked to 2 independent research groups, confirm that the telescope performed passive tracking of SWAN on November 17th and 19. The object fell within a scheduled deep sky window aimed toward Pisces, ironically, one of the constellations through which both SWAN and 3I-ATLAS were co-travelling at the time. Infrared returns were weak but detectable. According to the log files, Webb's sensors recorded mid-infrared emissions from SWAN's outer shell at a wavelength peak near 14.1 microns, consistent with low-temperature carbon dioxide outgassing. So, the question becomes, why didn't that trigger an alert? Under standard ESA NASA collaboration protocols, any non-catalogued body emitting structured mid-infrared radiation above background levels, especially if inbound toward the inner solar system, should be flagged for triage. A signal is then sent to the Minor Planet Center, and backup observations are requested from Earth-based assets. But none of that happened. There was no trigger, no alert, no follow-up request. Here's what the logs reveal. James Webb's onboard classification algorithm tagged SWAN as a non-priority thermal event. In other words, it saw the data, but filtered it out. This classification is based on an internal AI module designed to optimize observation time by rejecting noise, cosmic rays, and low-risk transient objects. Normally, that system is incredibly effective. It discards false positives like background galaxies mimicking motion, or low-energy asteroids emitting infrared spikes from solar flares. But in this case, it flagged SWAN as something else entirely. Non-volatile, non-rotating radiative decay. That's a specific tag. It means the object appeared to be leaking heat without rotation, fragmentation, or significant compositional variance. In essence, it looked dead, boring, inert, and not worth watching. But every other observatory disagrees. SWAN is accelerating, it's emitting polarization artifacts, it's displaying plasma symmetry and hollow core modelling, it is anything but inert. So, what went wrong? One theory is that Webb's filtering algorithm wasn't trained on interstellar objects of this behaviour type. Oumuamua, the first interstellar object ever recorded, never passed close enough for Webb to analyse, and Tui Borisov, the second, was already disintegrating by the time Webb's systems were calibrated. That means SWAN represents an entirely new category, one with no precedent in the telescope's training data. Another possibility is structural. James Webb is incredibly sensitive, but it's not a tracker. It has no active propulsion system and no way to rapidly pivot to fast-moving targets unless they're preloaded. SWAN, as an uncatalogued and low-albedo object, may have simply slipped under the system's radar until it was already gone. But the most whispered theory is strategic, that Webb's team didn't miss the data. They withheld it. Under internal security directives, Webb can down-prioritize objects whose classification triggers certain conditions, like unusual thermal layering, non-gravitational drift, or mirrored field structures already observed in other controversial objects. And SWAN, according to some quiet analysts, triggered all three. Whatever the cause, the outcome is the same. The world's most advanced space telescope observed a faint symmetrical heat-leaking interstellar object and said nothing. Not because it didn't see, but because it didn't know what it saw. In the early hours of November 28th, something unusual happened inside a small but critically important facility located in the Canary Islands. The TIDA Solar Observatory, typically focused on real-time solar imaging and magnetometry, recorded a brief but highly unusual spike in off-axis thermal energy, originating not from the Sun but from deep space, more specifically from the area between 3I-ATLAS and the SWAN object. What's strange isn't just what they recorded, it's that they didn't publish it. First, the basics. The TIDA Solar Observatory, TSO, operates a set of instruments that include coronagraphs, heliometers, and a solar radio spectrometer. While these tools are designed primarily for observing solar flares and coronal mass ejections, they also pick up high-frequency scatter and thermal shifts in objects that pass near the solar limb. On November 28th at approximately 0416 UTC, the observatory logged an anomalous thermal bloom in its sideband infrared layer. Brief, symmetrical, and triangulated across two observation angles. It wasn't a flare. It wasn't a solar artifact. It came from an external source, and it moved. The signal lasted 39 seconds. It rose sharply, plateaued, and then collapsed into background noise with no afterglow. The emission signature corresponded to mid-range infrared wavelengths, particularly in the 8.4 to 11.2 micron range. This range is typically associated with warm dust or gas ejecta, but there were no observable particles, no shadowing, no cometary outburst. So, what was it? Astronomers working inside the TSO quietly flagged the data as non-attributed thermal signature, meaning it didn't match any known solar or instrumental effect. But here's the part that raises eyebrows. The signal matched the triangulated midpoint between the paths of 3I-ATLAS and SWAN, and at that exact moment, both objects were positioned in near-parallel vectors, less than 1 degree apart from Earth's point of view. This was more than coincidence. According to two internal sources who reviewed the raw telemetry, the emission had a geometric waveform. In simplified terms, the intensity rose and fell in a way that suggested modulation, intentional or not. This wasn't a random heat spike. It had structure. It resembled a signal. And yet, nothing was published. The usual protocol when an observatory logs unexplained thermal data is to forward it to partner institutions and publish a short anomaly report in the International Astronomical Union's Transient Name Server, TNS. But no such report exists for this event. No external teams were notified, no follow-up scans were requested, and when queried by journalists 2 days later, the TSO responded with a single-line statement. No anomalous solar activity was detected during that window. That wasn't the question. Theories emerged fast. Some believe the spike was a byproduct of an energy transfer between the two objects, a form of ion exchange or localized magnetic coupling. Others have suggested the presence of a third unseen body that momentarily radiated and then disappeared. A handful of more radical voices suggest it was a short transmission burst, possibly even a failed communication attempt. But without official publication, the data sits in limbo, real but unverified, seen but not acknowledged. Why the silence? Some attribute it to the observatory's funding structure. The TSO receives both public and private support, including from aerospace defense contractors who have veto power over certain forms of data disclosure. Others point to internal caution. Without knowing what caused the spike, the team may have opted to withhold it to avoid premature panic or reputational risk. But there's another possibility, that the observatory knows exactly what it saw, and that it didn't fit any known framework. In science, silence is rarely the absence of data. It's often the presence of uncertainty, and the fear of what that uncertainty might reveal. Whatever emitted that signature, be it gas, energy, or something entirely different, did so from a location that should have been dark and quiet. And the fact that it wasn't published tells us one thing. The story isn't over, it's just not being told. On the surface, alignments in space aren't rare. Planets align, moons align, comets cross orbital planes. But when three bodies, two of them interstellar and one of them the Sun's invisible equatorial magnetic field, enter a perfect configuration over Earth's orbital plane, astronomers stop calling it coincidence, and they start calling it a pattern. That's exactly what happened in the pre-dawn hours of November 28th, when orbital tracking systems recorded an improbable, geometric relationship between 3I-ATLAS, the SWAN object, and the heliomagnetic equator, the fluctuating magnetic midline of the Sun. At first, it looked like a standard ecliptic coincidence. Both objects were already travelling through the same general sector, loosely aligned with Earth's orbital path. But when the solar magnetogram data from the Wilcox Solar Observatory was layered over the trajectory plots of ATLAS and SWAN, a strange correlation emerged. Both objects were positioned equidistantly on either side of the Sun's equatorial magnetic field, forming a precise tri-point alignment that stretched millions of kilometres, yet obeyed geometric tolerances within less than 1% deviation. This was not expected. Let's unpack what the heliomagnetic equator actually is. Unlike the Earth, the Sun's magnetic equator doesn't stay still. It shifts with the solar cycle, warping and tilting as the solar dynamo flips polarity every 11 years. This equator is essentially the balance line where the Sun's northern and southern magnetic hemispheres interact. It's invisible, but its influence extends far beyond the solar surface, carrying charged particles, modulating solar wind, and shaping the heliospheric current sheet, like a vast electromagnetic ribbon. So when two separate interstellar objects align themselves with this dynamic, shifting field, not just visually, but magnetically, something is off. Space physicists call this electromagnetic coupling potential. In simpler terms, it's when bodies moving through space respond not just to gravity, but to magnetic structures around them. Most natural objects, asteroids, comets, even small moons, do not display this behaviour unless they're embedded in magnetospheres or interacting with charged environments like Jupiter's radiation belts. But neither 3I-ATLAS nor SWAN are anywhere near a planet. They are far out in interplanetary space with no strong magnetic influence, except the Sun itself. The fact that both of them are interacting with the heliomagnetic equator at the same time, from opposite vectors, suggests that either their internal structure is magnetically responsive, or something else is coordinating them. The three-way alignment isn't merely symbolic, it has observable consequences. Data from the Solar Dynamics Observatory on November 28th revealed a subtle distortion in the solar current sheet during the alignment window. The sheet, which normally exhibits a slow, undulating wave pattern, briefly tightened, as if being pulled, taut by magnetic tension. This kind of shift typically occurs during solar flare activity, or large coronal mass ejections. But there was no flare, no CME, no sunspot cluster in sight, just a magnetic field stretching itself toward two faint interstellar objects, both of which were emitting polarized plasma fields and showing signs of synchronous energy fluctuation. There's more. Ground-based magnetometers in Chile and South Africa recorded microvariations in geomagnetic background noise during the exact hour of the alignment. Though small, barely above statistical noise, they formed a repeating pattern spaced at nearly identical intervals, 11.2 minutes apart. This frequency is not associated with solar rotation or Earth's Schumann resonance. In fact, it doesn't match any known natural periodicity in the region. Some researchers speculate this may be a side effect of magnetic field entanglement between the Sun and the two objects, a kind of harmonic resonance. Others whisper more speculative ideas, energy transfer, signal mirroring, or even positional calibration between artificial structures. No one's making that claim officially. But the numbers are there, the angles match, the alignment occurred, and something in the Sun responded. In deep space physics, alignment is never just about position. It's about influence, who's pulling on what and how. And on November 28th, for exactly 47 minutes, the Sun's most chaotic field, its magnetic equator, formed a perfect line through two silent objects that should have had nothing in common, except that now they do. When astronomers study comets or interstellar objects, one of the first calculations they run is the energy budget. It's a foundational principle in astrophysics: how much energy is coming in, how much is being converted, and how much is being radiated out. These simple numbers reveal an object's behaviour, whether it's heating up, shedding mass, or undergoing internal changes. But with the SWAN object, and increasingly with 3I-ATLAS, something is fundamentally broken in that budget. On the morning of November 28th, observatories across 3 continents reported elevated outgassing rates from SWAN's outer layers. The primary components, carbon dioxide, carbon monoxide, and trace ammonia, were detected in significant quantities. Based on spectroscopy from both the VLT in Chile and the Subaru telescope in Hawaii, the outflow rates suggested that hundreds of kilograms of material per second were being ejected. That level of sublimation would normally produce a tremendous thermal signature, visible in mid-infrared bands with a noticeable tail or plume. But SWAN didn't show any of that. It remained visually muted, dimmer than expected, and thermally inconsistent. So where's the energy going? Let's walk through the math. According to solar flux calculations at SWAN's distance from the Sun, approximately 1.4 astronomical units, it should receive about 963 watts per square metre. Given its estimated surface area, roughly equivalent to a 300-metre wide sphere, the total solar input energy would be in the range of 2.7 megawatts. That energy, if absorbed even partially, should heat the object enough to sublimate gases and re-radiate the rest as heat. Instead, what we observe is this. The gases are escaping at the expected chemical rates, but the emitted thermal radiation is missing. Instruments like NEOWISE and the Infrared Survey Facility detect a faint glow, but nowhere near the levels that this outgassing should produce. This mismatch raises a dangerous possibility. One explanation is internal heat retention. In this model, SWAN could have a subsurface shell or matrix that captures and stores thermal energy, re-radiating it at a much slower rate. This behaviour is not unheard of. Certain dense comets retain heat for hours or days before emitting it. But those objects typically show heat leaks, hotspots, or surface cracking. SWAN does not. Another theory is anisotropic emission, meaning the object is radiating heat directionally, but not toward Earth. In other words, it may be shedding energy in a beam or focused pattern, invisible to us unless we were in the path of the emission. That would require a high degree of control over thermal gradients, something rarely seen outside engineered systems. A more radical idea, gaining traction in closed circles, is that SWAN is converting thermal input into non-thermal outputs, like magnetic or electrostatic fields. That would explain its stable plasma bubble and the containment of ionized gases seen in previous chapters. If the object is bleeding off heat as electromagnetic structure instead of infrared radiation, it would maintain a cold exterior while still powering out gassing. But the most uncomfortable conclusion is this. The numbers might not be wrong, the assumptions might be. What if the outgassing isn't caused by solar heating at all? What if SWAN is internally powered? In that case, the object isn't shedding heat, it's releasing pressurized gas through an internal mechanism. That would account for the elevated outflow rates without corresponding surface warming, and it would imply internal chambers, pressure gradients, and some form of regulation, mechanical, geological, or otherwise. 3I-ATLAS showed signs of similar behavior earlier this month. As its coma expanded, thermal models showed colder than expected readings, even as gas flow increased. Now SWAN is doing the same thing, but more cleanly, more precisely. This isn't a comet with poor insulation. This is an object where energy input, energy output, and energy transformation do not match, by a factor of 10 or more. In physics, energy doesn't disappear. It moves, it hides, it transforms, and if we can't find it in light or heat, we have to ask, where is it going, and what is it powering? On the morning of November 28th, a brief infrared anomaly recorded by 3 independent observatories sent a quiet but measurable tremor through the astrophysics community. It wasn't an explosion. It wasn't a flare. It was something more delicate and more difficult to explain. A perfect spherical collapse, captured in the 12 to 16 micron band by thermal imaging sensors at the Cerro Tololo Inter-American Observatory, CTIO, in Chile. The anomaly lasted just 18.4 seconds. It appeared in the region of space where the SWAN object had previously been plotted, though no visible tail or structural signature was recorded during the event itself. What the instruments picked up was a subtle, concentric pattern of infrared intensification, lightly pulsing from the centre outward in exact spherical symmetry, then vanishing. This type of thermal behaviour isn't new in astronomy. Collapsing gas clouds, imploding stellar cores, or even planetary atmospheric disturbances can create spherical waves. But those are usually chaotic, asymmetrical, or turbulent. What made this one different, almost elegant, was its precision. The emission pulse formed a mathematically perfect sphere. expanding evenly in all directions at a rate of approximately 91 kilometers per second, then contracting back into silence without residue. In simpler terms, the object pulsed outward, then disappeared. The anomaly was independently confirmed by mid-infrared spectrometers at the Mauna Kea Observatory in Hawaii and the Gran Telescopio Canarias. Both sites captured time-synced data showing the exact same spherical progression, same radius, same intensity decay, same central coordinates, what collapsed, and why. That's where the theories begin to splinter. One hypothesis is that this was the final structural disintegration of a hollow core, consistent with the internal void theories surrounding both SWAN and 3I-ATLAS. If SWAN's interior was composed of a layered shell, thin, under pressure and electromagnetically stabilized, it's possible that an internal failure caused the entire structure to implode uniformly, like a submarine crushed at depth, only in vacuum and silence. But that doesn't explain the lack of debris. No secondary fragments were detected, no cometary particles, no residual heat cloud, just a pulse, and then nothing. If this were a physical object collapsing under pressure, some material should remain. That's where a second, more radical theory comes in, non-material containment loss. In this model, SWAN was not a fully solid object. It was a shell, a spherical containment of plasma, magnetism, or radiation. The collapse wasn't physical, but electromagnetic. When whatever force was maintaining that spherical structure failed, be it internal power, solar interaction, or proximity to 3I-ATLAS, the energy field retracted into its null state, releasing a symmetrical echo of heat as it did. This behavior has precedent, but not in space. It's similar to what happens in laboratory tests of plasma containment bubbles, like those seen in tokamak fusion reactors. In those settings, when the containment field fails, the plasma releases in a symmetric pulse, short, intense, and entirely spherical. What makes this idea even more unnerving is that SWAN's pulse came with no radial drift. The sphere expanded evenly without tilting, drifting, or smearing. That suggests a centre of symmetry that was perfectly stable in space, a behaviour rarely seen in natural outbursts. Another possibility, temporal discharge. While entirely speculative, some researchers have begun exploring whether the infrared pulse may represent a rapid energy shift not just through space, but across timeframes of interaction. In this view, SWAN's core may have held a tension or charge that collapsed in a frame decoupled from normal gravitational motion, releasing a symmetrical field response. This is the realm of field theory, hypothetical, but grounded in real math. The broader implication? If a structure can collapse like this, perfectly spherical, heat-silent and residue-free, it wasn't built randomly. It was built to maintain symmetry, and whatever symmetry held it in place, let go. Not violently, not catastrophically, but cleanly, like a mechanism turning off. Infrared echoes don't lie. They reveal structure long after the visible trace is gone, and in this case, they reveal the fingerprint of a presence that understood precision far beyond what comets are known for. It didn't shatter. It vanished, with intention. If either 3I-ATLAS or the SWAN object were to fragment while in Earth's neighbourhood, the first and most visible concern would be orbital debris. But beneath that obvious threat lies a more complex and less discussed scenario: atmospheric seeding. This idea isn't science fiction. It's a documented possibility that's part of planetary defence modelling, especially when dealing with exotic materials entering Earth's upper atmosphere. When an object fragments near or within the exosphere, it doesn't always produce flaming trails or recoverable meteorites. Sometimes the debris remains small, micron-sized particles or nanoparticulate dust, and these particles don't burn up. They disperse, and if they contain volatile compounds, reactive isotopes, or electrostatic properties, they can integrate with Earth's upper atmosphere, quietly, invisibly, and with consequences we don't fully understand. So what does the data from November 28th suggest? Let's start with orbital positioning. At the time of the observed infrared collapse, covered in Chapter 14, SWAN was travelling at approximately 63 kilometers per second. That velocity, combined with its inward trajectory near the ecliptic plane, placed it on a shallow intercept course with Earth's orbital path, Not a direct hit, but close enough that any fragmentation event would produce a diffuse cloud of debris spreading across a significant arc. If even a small fraction of that material were to intersect, with Earth's atmosphere, the particles would likely enter at low angles, skipping across the upper thermosphere before settling, or remaining aloft for extended periods. At that altitude, they wouldn't burn up or fall, they'd mix, with ozone, with charged ion layers, with solar wind interfaces. Now let's talk about composition. Spectroscopy from the Subaru telescope earlier in the month revealed trace elements in SWAN's coma, not commonly found in traditional comets: iridium, tungsten, and technetium. The first two are dense, rare metals often associated with industrial processes. The third, technetium, is radioactive and does not occur naturally on Earth except as a byproduct of fission. While the spectroscopic signature was weak, the very presence of these elements raises the stakes. What happens if a particulate cloud seeded with these materials enters Earth's atmosphere? Atmospheric chemists worry about ionospheric disruption. These exotic particles could alter conductivity in the D and E layers of the atmosphere, potentially affecting GPS accuracy, shortwave radio propagation, and even satellite drag calculations. It wouldn't cause chaos overnight, but it would scramble the models we rely on. Then there's the biological risk. If any of the material reaches the stratosphere, either through gravitational settling or electrostatic lofting, there's a hypothetical chance that foreign isotopes or reactive particles could interfere with cloud nucleation, UV absorption, or even microbiological balances in high-altitude layers. While no direct evidence supports biological impact from interstellar particles, yet recent research on diatoms and extremophiles surviving in the upper atmosphere suggests Earth is more porous than we thought. And what about tracking this? That's the issue. Nanoparticulates don't show up on radar. They don't reflect visible light well. They're invisible to traditional satellite imaging. Once in the atmosphere, they behave more like dust than debris, diffusing slowly, guided by temperature gradients and jet stream currents. The European Space Agency's GRACE-FO satellites detected a minor change in gravitational density along Earth's upper atmosphere 10 hours after the SWAN pulse. The data isn't conclusive, but it's suggestive. A small, fast-moving mass passed near Earth's gravitational envelope, shedding density, then disappearing. No trackable object remained. That's consistent with a diffuse cloud of exotic dust. To be clear, this isn't a doomsday scenario. There's no evidence of poisoning, mass ionization, or planet-wide fallout. But the presence of technetium in an inbound interstellar object is enough to raise every eyebrow in the room. If these objects fragment, intentionally or accidentally, Earth doesn't just get a show in the sky. We get seeded, quietly, chemically, with materials we cannot easily model. And the scariest part isn't what we know, it's what we can't detect, until it's already here. When dealing with interstellar anomalies like 3I-ATLAS and SWAN, scientists often look to telescopes, probes, or direct images for answers. But sometimes, the real anomaly hides in the metadata. That's exactly what happened in a quiet corner of NASA's publicly accessible heliophysics data logs, specifically within the Deep Space Network, DSN telemetry timestamps, and the solar wind analysis feeds archived from November 28th. It was a graduate researcher at the University of Colorado Boulder who first spotted it. While cross-referencing solar wind velocity patterns and object tracking telemetry, she noticed something strange. Between just 3:24 and just 3:41 UTC, nearly a dozen timestamped entries across 4 independent instrument streams all recorded a temporal deviation of precisely 0.773 seconds, not in clock time but in the phase of recorded data packets. These data streams, coming from sources like ACE, Advanced Composition Explorer, SOHO, Solar and Heliospheric Observatory, Parker Solar Probe and even the Wind Satellite, are independently clocked. Their internal timing systems are regularly synchronized with GPS and the DSN's ultra-stable oscillators. Under normal conditions, these systems never deviate from each other beyond a few microseconds. But on November 28th, they did. For 17 minutes, the time-phase data packets from these spacecraft appeared to slip forward, not permanently, but momentarily, and always by exactly the same interval, 0.773 seconds. This is now being referred to internally as the synchronization artifact. Here's what makes it disturbing. All four streams were logging measurements of solar wind density and interplanetary magnetic field, IMF, vectors at the moment of the anomaly. But the spikes in timing occurred before any meaningful change was recorded in the solar environment, suggesting the phase shift wasn't caused by solar variation, but by an external timing influence. To put it plainly, something synchronized these spacecraft sensors without touching their internal clocks. The effect occurred only in the phase alignment of the incoming data, not in the actual telemetry timestamps. It's as if an external pulse caused multiple instruments, at different locations in the heliosphere, to momentarily align, like a conductor cueing an orchestra. Some scientists propose a natural explanation, a perfectly timed solar microburst perhaps, with high enough coherence to register simultaneously across multiple satellites. But no solar event, no flare, no CME, no magnetic anomaly was detected at that time. The sun was calm. That leaves a second theory, external synchronization via non-electromagnetic coupling. In this view, a low-frequency gravity wave or a magnetoacoustic pulse, emitted not by the sun but by one of the interstellar objects, could have created a transient resonance across the DSN sensor arrays. This theory, while unconventional, is supported by the triangular geometry that existed at the time. Both 3I-ATLAS and the SWAN object were nearly equidistant from Earth and the Sun, positioned at vectors that would allow a shared field or pulse to pass through Earth's orbital position and affect multiple satellites at the same time. The artifact only lasted for 3 data cycles. Then, as quickly as it appeared, the synchronization disappeared. NASA has not issued a formal statement. However, a quiet revision was made in the November 29th log. A footnote was added to the data file headers, noting phase irregularity detected under review for clock calibration artifacts. No follow-up report has been published, but those who monitor such data know better. Calibration errors don't align across 4 spacecraft at once. Random noise doesn't yield identical intervals, and phase shifts this clean don't appear without cause. The question isn't whether the data glitched. The question is what tried to synchronize it, and why. In astrophysics, synchronization is a hallmark of systems. Binary stars sync, planets and moons sync, artificial systems sync. When instruments begin to do the same, without a source, we're left with only 2 options: coincidence or contact, and neither answer is comfortable. Astronomers are trained to see patterns, but also to doubt them. In deep space, symmetry often collapses under scrutiny. What looks like a circle is usually an ellipse. What seems aligned is usually the result of perspective. But on the morning of November 28th, the geometry between 3I-ATLAS, the SWAN object, and Earth entered a configuration so statistically elegant that even the skeptics hesitated. It wasn't just that the 3 bodies formed a triangle, it was that the triangle was perfect, to within 0.03 degrees of equilateral symmetry. In that moment, at 0542 UTC, the line between Earth and 3I-ATLAS matched the distance from 3I-ATLAS to SWAN, and from SWAN back to Earth. When plotted, the coordinates formed a closed-loop symmetry centered almost precisely on the solar ecliptic. And more unnervingly, the rotational vectors of both 3I-ATLAS and SWAN were recorded as being counter-rotational, but synchronized in angular velocity. In other words, they were spinning in opposite directions at the same rate. This should not happen. Celestial mechanics dictate randomness in object orientation. Interstellar bodies are chaotic. Their spin axes, speeds and paths are shaped by billions of years of collisions and gravity wells. Even binary stars, formed from the same molecular cloud, don't typically rotate in perfect sync. But here, on a trajectory thousands of light years long, 2 foreign objects entered our solar system and mirrored each other. This geometric resonance triggered quiet conversations behind the scenes. At the European Southern Observatory, a team reprocessed radar reflectivity maps and discovered something even stranger. Both 3I-ATLAS and SWAN had matching radar, silhouettes, differing only in scale. 3I-ATLAS appeared roughly 41% larger, but the contour structures of the objects, jagged protrusions, cavity depths, and reflective signatures, followed the same pattern, as if one were a scaled copy of the other. If this were discovered in terrestrial materials, 2 objects of different size made of different substances, but shaped identically, it would immediately trigger investigation into manufacture. In astronomy, that kind of alignment is often dismissed as coincidence. But when it happens in deep space between two interstellar visitors sharing proximity, angular velocity, and geometric symmetry, the conversation shifts. The notion of intentional design isn't new in astrophysics. It forms the backbone of SETI, Search for Extraterrestrial Intelligence, where researchers listen for signals that show non-random structure. Mathematical symmetry, prime numbers, phase-locked pulses, these signs separate noise from message. Nature, after all, is rarely perfect. But machines are. The alignment of 3I-ATLAS and SWAN may not be mechanical, but it raises the unsettling possibility that what we're seeing isn't natural formation but programmed trajectory, that these objects were released, guided, or nudged into this configuration for a purpose, whether observational, energetic, or something else entirely. Some theorists suggest a concept called resonant insertion, a form of gravitational harmonization in which an object is designed to follow the orbital pathways of another, eventually creating moments of alignment where energy, data, or material can be exchanged with minimal interference. In physics, this is seen in Lagrangian points, regions of balanced gravity. But this triangle wasn't at a Lagrange point, it was moving. The apex of the triangle, the point where all three bodies aligned, passed briefly over Earth's upper southern hemisphere. Ground-based magnetometers in Argentina, South Africa and Western Australia all recorded low-frequency anomalies at the time of alignment. Not high enough to trip alarms, but real, timed, structured. So what do we make of it? There are only two rational conclusions. One, we have witnessed the rarest type of cosmic choreography, a 1,000,000,000 to 1 alignment that mimics intelligent pattern, a reflection of chaos that just happened to look like order. Or two, we've seen something built, not in the mechanical sense, but in motion, in structure, in behaviour. An echo of intention, moving through space not because of gravity, but because of design. In either case, the meaning is the same. Something passed through our solar system on November 28th that understood geometry better than we do, and it left behind a shape no one can explain. In the world of astrophysics, silence is data. A lack of emissions, a missing signal, a flat line in expected spectrums. These are not gaps in the record. They're often the record itself, and when dealing with deep space phenomena like 3I-ATLAS and the SWAN object, silence can say more than transmission. On November 28th, following the geometric alignment of the two interstellar bodies and Earth, a team of researchers at the Deep Space Communications Complex in Canberra attempted a routine passive scan of the region using broadband radio interferometry. The goal was straightforward: collect wideband emissions across the X, K and L bands to see if either object reflected or emitted any natural radio activity as they crossed Earth's orbital plane. They got nothing, but not just low signal, not just white noise. What they recorded was a full band radio null, an absolute flatness across all expected frequencies, with no atmospheric or background interference. This is rare. Even the coldest objects in space reflect or scatter some level of ambient radio frequency energy. What the Canberra team observed was deliberate quiet. Radio silence in natural settings occurs for one of three reasons. The object is too small, cold, or inert to reflect or emit signals. The object is shielded by distance, angle, or composition from detectable frequencies. The object is actively dampening or absorbing signal emissions. The first possibility doesn't fit. Both 3I-ATLAS and SWAN have shown significant plasma interactions, outgassing events, and infrared behaviour, far from inert. The second is unlikely. Earth-based observatories were positioned almost perfectly along the shared orbital corridor. If these objects had ordinary surfaces, we should have seen background scatter from solar emissions bouncing off their structures. That leaves the third option: active silence. There is a known concept in electronic warfare and stealth technology called emission control, or EMCON. Submarines, stealth aircraft and satellite arrays use this to avoid detection by minimizing their own electromagnetic footprint. But the most advanced forms of EMCON go further. They cancel or absorb surrounding emissions, creating a bubble of radio invisibility. Could 3I-ATLAS or SWAN be exhibiting a natural form of EMCON? Some suggest that highly porous materials combined with specific plasma field arrangements could form non-reflective surfaces in certain frequency bands. It's not impossible. but to maintain that across all major observation bands, including ultra-low VLF sweeps, requires either design or the most improbable material coincidence known to astrophysics. But here's the critical piece. The silence was timed. The radio null lasted for a 44-minute window during the alignment event. Before and after, weak scatter returns resumed. It was only during the equilateral triangle alignment, when both objects were in geometric symmetry with Earth, that the radio bands went dead. This suggests coordination, or at the very least conditional behaviour. Either the silence was a response to environmental configuration, or it was part of a programmed state within one or both objects. In either case, silence became behaviour, and then came the anomaly. During that same window, two low-Earth orbit satellites, Aqua and NOAA-20, recorded microbursts of thermal bloom in the upper ionosphere. These bursts were brief, hemispherically distributed, and had no solar driver. They were, however, synchronous with the radio null. In classified systems, there's a phrase, dark comms, communication that occurs in non-traditional spectrums, often masked or encrypted in thermal, gravitational, or optical distortions. If something was speaking during that silence, it didn't use radio. It may have used heat, or field interference, or geometry. But it didn't want to be heard in the conventional sense, because sometimes silence is not a lack of communication, it's the message itself. It says, I'm here, I'm aware, and I choose not to speak where you are listening. In the theatre of celestial mechanics, Earth's Lagrange points are the quiet backstage, regions of gravitational balance where the forces between Earth and the Sun cancel each other out. These 5 locations, L1 through L5, form gravitational equilibrium zones, and they serve as ideal stations for satellites, observatories, and in theory, any object that needs to hover with minimal fuel. But on November 28th, during the unusual proximity of both 3I-ATLAS and the SWAN object, a subtle but deeply telling shift occurred near L1 and L2, the most sensitive and closely monitored Lagrange points. It began as a drift, detected first not in visible light, but in the gravitational mapping telemetry from ESA's LISA Pathfinder and NASA's DS-GOVA probe. These two observatories, both situated near L1, began reporting anomalous changes in their microthrust stabilization data. In simple terms, they were having to correct for forces that shouldn't have been there. At first, the deviations seemed minor, fractions of a Newton in stabilizing thrust, but the timing revealed something deeper. The moment these adjustments became necessary correlated precisely with the approach of the SWAN object toward Earth's side of the Sun, at a distance of just over 0.3 AU. Then came the deeper anomaly. Near L2, which sits behind Earth's shadow, shielded from the Sun and home to the James Webb Space Telescope, a similar drift pattern began, but this time the force vector was not solar. It was subtle, off-axis, and changing in phase. Instruments onboard JWST didn't register a visual target, but they did report minor gyroscopic compensation events, almost like the telescope was being nudged off its pointing vector ever so slightly. So what was causing it? The working theory hinges on a phenomenon known as gravitational interference drift. While Newtonian gravity is smooth and predictable, general relativity allows for field distortions, especially in the presence of objects with unusual mass distribution or exotic velocity profiles. If either 3I-ATLAS or SWAN contains non-uniform internal density, such as a hollow core, concentrated mass shell, or embedded heavy element structure, it could distort gravity fields not just locally, but over vast distances due to relativistic propagation. In simpler terms, even without being close, the shape and motion of an interstellar object can create ripples of uneven gravitational influence, enough to unbalance spacecraft that live in these knife-edge equilibrium points. But there's another, less comfortable interpretation. What if the drift wasn't a side effect? What if it was a test? Lagrange points, especially L1 and L2, are choke points in Earth's observational infrastructure. L1 monitors the Sun, L2 watches the stars. If one were to evaluate how Earth's defense systems, satellites or telescopes respond to subtle changes in force, those would be the places to probe. The data from both points suggests the disturbances were not constant. They rose and fell in phase, almost like a pulsed wave, lasting for just under 11 minutes, not long enough to trip emergency protocols, but enough to trigger manual review. And buried deep in those reviews was another oddity. The gravitational drift vectors at L1 and L2, when plotted, pointed not toward 3I-ATLAS and not toward SWAN, but toward a mathematical midpoint between them. That midpoint had no known object, no visible body, no radio source, but it had gravity, enough to create measurable effects, enough to nudge precision-stabilized instruments, enough to cause LISA Pathfinder to activate fallback attitude control, something it has not done in over 700 days. What does this mean? At minimum, it tells us we're dealing with unconventional mass behavior, objects that do not distribute gravity the way we expect. At maximum, it suggests the presence of an additional unseen object hidden between 3I-ATLAS and SWAN, exerting just enough force to be noticed, if you're watching the right place. The Lagrange points are not just passive zones of balance, they're pressure points. And on November 28th, someone or something pushed them. On the surface, the Sun looked quiet on November 28th. No solar flares, no coronal mass ejections, no X-class bursts. But when the heliophysics logs from NASA's Solar Dynamics Observatory were reviewed in detail, a quiet undercurrent of structural reversal was detected in the Sun's magnetic scaffolding. A shift, not explosive, but fundamental. It began at the equator. At 0706 UTC, magnetogram data showed a polarity inversion ripple forming across the solar surface, particularly in the western hemisphere. It wasn't immediate, it wasn't violent. But over the next 48 minutes, the data showed a slow phase drift in the heliospheric current sheet. The invisible structure that shapes the solar wind, the heliopause, and even Earth's magnetosphere. This shift is being referred to internally as a first-phase heliophysics reversal. What does that mean? The Sun's magnetic field flips, roughly every 11 years. It's part of the normal solar cycle. North becomes south, south becomes north. But that reversal is usually gradual and global. What happened on November 28th wasn't part of that cycle. It was localized, accelerated, and, according to all existing models, too early. So what triggered it? There are two prevailing theories. The first suggests that the approach of 3I-ATLAS and SWAN, both on paths that slice through the solar system's equatorial plane, may have perturbed the magnetic topology of the Sun itself. While these objects are small compared to the Sun, their combined electromagnetic signatures, strange albedo ratios and synchronized velocities may have created a resonance effect, pushing the heliospheric current sheet to flex and momentarily realign. The second theory is far more unsettling. It posits that we are witnessing the first phase of a non-cyclical reversal, that something, internal to the Sun or external to the system, has interfered with the solar dynamo process, causing the magnetic field to begin breaking symmetry in a non-natural pattern. If that's true, then what we saw on November 28th was not the Sun flipping its field. It was the Sun being flipped. There is precedent for this. In 1893 and again in 1958, solar observatories recorded sudden and unexplained shifts in the Sun's magnetic orientation, followed by geomagnetic storms on Earth weeks later. Those events were retroactively labelled as solar anomalies, but the records match what we're seeing now: an initial surface ripple, followed by current sheet drift, and then realignment. Except this time, the drift isn't reverting, it's deepening. Already, solar probes like Parker and Ulysses are reporting unexpected magnetic inversion zones, not only near the Sun's equator, but also along off-axis latitudes. These zones aren't stable, they're rotating. And that's what makes this dangerous. If the Sun enters a state of non-axis symmetric magnetic inversion, the entire structure of the heliosphere could become unstable. That means the shape of solar wind emissions could change, focusing energy in new directions, skipping normal deflection zones, and potentially exposing Earth to high-intensity particle storms without warning. Worse, these changes wouldn't be visible from Earth's surface. They would start silently, with magnetic ripples, with drift zones in the solar current, with field lines that refuse to connect, which brings us back to 3I-ATLAS and SWAN. Both objects have shown behaviours suggesting electromagnetic interaction, not just with each other, but with the Sun. Their tail geometries have shifted in response to nothing visible. Their trajectories have adjusted in ways that imply sensing, not reaction. If these objects are more than comets, if they are fields or constructs or coherent plasma systems, then their passage through the solar equator may not have been passive at all. It may have been the cause, And, if so, then we are not just observing a heliophysics reversal. We are witnessing the first stage of something larger, something that may redefine our understanding of stellar stability. Because the Sun is not just a star, it is the heartbeat of the system, and something may have just placed its finger on the pulse. At a distance of millions of kilometres from Earth, two interstellar objects, 3I-ATLAS and the SWAN anomaly, entered our system with heat signatures that mostly conform to expectation. Both were absorbing solar radiation, shedding mass through sublimation, and interacting with the solar wind. These are the standard thermal behaviours of icy, non-reflective bodies travelling through the inner solar system. But on November 28th, a brief and confounding detection flipped the script entirely. It began with the infrared survey instrument aboard the Neowise satellite, which was tasked with routine thermal scans along Earth's orbital path. During a cross-sweep of the region just past L2, a cold anomaly appeared in the data, a distinct region registering more than 80 degrees Kelvin below the surrounding interplanetary medium. It was, by all accounts, too cold to exist naturally in open solar space. At first, analysts believed it could be an instrumental artifact, a sensor malfunction, or an image processing glitch. But a secondary confirmation came in minutes later, this time from the Atacama Large Millimeter Array, ALMA, in Chile, which detected an ultra-low energy radiation gap in the same region of the sky. That kind of confirmation, from two independent instruments using different detection methods, instantly ruled out coincidence. There was something real there, and it was cold, colder than space itself. This is where the questions begin. Space is not truly cold in the way we think of temperature on Earth. The interplanetary medium sits at about 3 Kelvin, but it's filled with radiation, infrared, microwave, and solar flux. Most objects, even dark ones, absorb some of that energy and re-emit it, creating faint thermal halos. But the anomaly near SWAN showed thermal inversion. Instead of emitting heat, it seemed to absorb it, like a sponge drawing in background radiation. No comet, no asteroid, no chunk of rock behaves this way. Several models were run to simulate possible causes. One theory suggested a cloud of ultrafine dust, denser than previously known interstellar dust clouds, but somehow held in place around the object, absorbing heat from all directions. The problem? The geometry was wrong. The cold spot was not diffuse. It was sharply bounded, measurable in diameter, consistent over the observation window, and moving synchronously with the SWAN object. Then came the speculative theory that we were looking not at cold matter, but at a field, a structured zone of suppressed thermal activity generated by an active process. In laboratory physics, similar effects are seen in Bose-Einstein condensates, where atoms are cooled to near absolute zero and enter quantum states. On a macroscopic scale, though, this shouldn't be possible, yet the idea persisted. What if the SWAN object wasn't simply passive? What if it was shielded? Not mechanically, but thermodynamically. The implications are staggering. Such a field could be a form of radiation control, allowing the object to become effectively invisible to infrared scans, passive sensors, and thermal tracking systems. It would not reflect, it would not emit, it would exist as a thermal void. Worse still, the boundary of this cold zone showed subtle fluctuations, as if it were reacting to nearby solar wind variations. A passive object doesn't react to particle flows, a responsive field does. There's a term in stealth aerospace design called negative signature management, the concept of reducing not just visibility, but detectability itself across all known spectrums. On Earth, it's theoretical. In deep space, we may have just seen it in practice. If the SWAN object is projecting such a field, or is surrounded by a naturally forming but actively behaving thermal suppression zone, then we must question everything we thought we knew about its nature. Because in the vacuum of space, where everything radiates, a region that sucks in heat is not just an anomaly, it's an intentional silence. And that silence is colder than the void that surrounds it.